I record I record it on my computer so that I can upload it to our YouTube channel. Okay. So if you come to class, you can ask questions, and hear maybe some corrections or stuff. That would be one great reason to come to class, and at least have some periodicity in your day. If you accidentally miss class, get COVID and can't study, that's okay, because I record all the lectures, which are these live things. Plus, I have videos that are uninterrupted, that are directed at just getting the information as well from the slides and in the book, but it's not like the live lecture where I might focus on a particular aspect when I get a question. So you can use either one as a good tool. The book itself, I believe, is a very good tool. I think they explain things at the correct level. It's not too verbose. Some of the books just go on and on. My regular organic chemistry book has like 1,200 pages on it. It's like, come on, stop talking. Let's just get to the stuff. So this book does a very good job at sticking to what we have. Okay, so that's 51. That's, a good 80%. So I'm going to go ahead and start to share my screen here. And what I want to do is give you a tour of the TRACS website first, and then I want to, let me go ahead and share my screen. Share my screen and Chrome. There we go. So you should see this TRACS website up here now. I'm sorry, Canvas. Yeah, I still say TRACS for some reason. Canvas has a lot of advantages over TRACS, but TRACS, had a lot of advantages over that too, but we'll do this because we have it. All right, so welcome to Organic Chemistry 2330, Introduction to Organic Chemistry. I'm Dr. David Urban. My PhD is in organic chemistry. This is my chosen field. I really, really love it. I've been doing it over 30 years now. I've spent more than 10 years in academic laboratories, 10 years in government laboratories, including the Department of Defense and the Department of Energy. And I also spent another about 12 years in industry. And so I've probably actually run about 75% of the reactions you see in the book. So I come from a little bit different perspective from other lecturers, in the fact that I'm doing this to share my knowledge, but I also have done a bunch of different things, everything from building multi-million-dollar machines to synthesizing the strangest of explosives. So I have this broad range of experience in the field of organic chemistry, and I'd like to share those experiences with you. So a lot of times I'll give an actual experiment that I ran and give you a little bit more detail about it. And so that might come up from time to time. So there you go. So one of the things I've changed this semester is that I have all of my stuff is going to be on the Canvas site like this. And I've added buttons to make it easier for you to navigate from place to place to place. For example, if you go to this and click the live lectures button, that will be that week's Zoom connection with the password. So you should be able to just click that and it should take you directly to our live class. And then as soon as I chime in, as soon as I log on, we'll do that. So that's a great way to do that if you are using it for that. If not, go ahead and go to that live lectures tab, open it up, and then copy and paste that meeting code if you're going to use a phone or an iPad or something like that. So that's another way to do it. What I will also do, I'm probably going to start in the announcements, I'll actually add the code for that week. If you're not using Canvas to do this negotiation, you can just go to the announcements and be able to copy and paste that onto whatever platform you're going to use. Okay, so the second tab here is our lecture videos tab. And what that's going to do is that's going to take you to the YouTube channel that's just for our in-class lectures, okay? So these in-class lectures are going to be recorded. They're going to have mistakes. There's going to have comments and questions, and that's where you're going to find this. So if you miss class, this is the place to go. Or if you're reviewing your notes and you're like, hey, I didn't write that down correctly, or that doesn't sound right, you can go ahead and go back to the video and look at that. So that's one opportunity if you miss a class, if you get COVID, if you just don't feel good that day. Okay. So those will be posted approximately 30 minutes after class. Today's going to be a little later, but because it's taking a little bit longer to process today. The next thing we have here is our homework tab. And our homework tab takes us to our Top Hat site. So the Top Hat site has both copies of all our slides, it has our homework assignments, and this is where we're going to be taking our exams, okay? So notice that right now I have assigned all of the chapter homeworks and the slides for the first 5 chapters or so. So you can start reviewing these things. The slides I'll be using in class are the ones that are right here that aren't the goal slides. The goal slides are condensed versions of just specific subtopics that I would like to, if you're having trouble with a particular topic, those goal slides, if that topic is one of those things on there, it gives a nice description of how it's done. Okay, so then our homework is here, reviewing slides are here, and I will be presenting from here. So what I'm going to do is when I come and start doing the actual lecture, I'm going to unassign this, I'm going to lecture through Top Hat, and then I will reassign it at the end of class. Okay, so let's say you don't want to do that. Well, that's fine. If you go to our Canvas site and look under our resources tab here, you can also find all of these slides under the slides video selection. And so these are all broken down by chapter, and that's all the slides for everything. So if you wanted to download them ahead of time or have them on your iPad and annotate as you go, that's a great way to do it. In fact, I used to lecture the class by downloading it was actually a PDF to my iPad. I could annotate it, it would save all my notes. So that's a good way to take notes on it if you want to do that. So that's also available to you. And then going along on our buttons here, we have activities. We're going to have at least one activity. I'm trying to get a couple more in here that are just kind of group activities where we break off into small, let's see, what are they called? Breakout rooms of like 5 or 6 people, and you just kind of talk about the chemistry and kind of work the problem together. I figured number 1, it's slightly social. Number 2, it lets you hear from other students and lets you kind of get a peer-to-peer perspective on there. I have at least one plan. I'm trying to squeeze in a second one to make sure it works. There's also the lecture and exam schedule, which obviously I need to fix. The one here in the table is probably the most correct one. I will fix it in the syllabus as we go. And then there's the syllabus page. Resources is where all of the different things are. Included in that are things like the chapter reviews for each of the exams are in these different sections here. In addition to that, there's also the nomenclature review. So the nomenclature review is something that we'll hit on from time to time, including before exams, so that you'll be able to kind of like remember what we're doing by the end of the exam, by the end of the course. All right, so then the last thing here is what I call the full videos right here. Okay, so these are the videos of all of the different chapters broken down into smaller bites. There's a couple longer ones that are 30 minutes, but I try to keep them shorter than that. This is the entire book. This is the full slides broken down into individual things where I have gone and written and annotated, but there's no interruptions. They're recorded separately. So if you miss a topic or you miss a chapter, you might want to go back to these, look at the whole thing, and then have that as a secondary source for learning the chemistry. I probably tell different stories or just explain it in a slightly different way in these slides. So if you didn't quite get my explanation, you might want to go to this and see if that helps. If not, go ahead and email me and we'll set up a time for office hours.
I'm sorry, what button did you say that's for? Or what button is that one?
The full videos button is the entire book broken down into shorter videos. The lecture videos are the live action stuff that we have here. Okay. So, and then there's the syllabus here. I believe everything in the syllabus is correct. I might have to change the grading scheme a little bit, but I think that's for the most part good. All right.
Okay, thank you so much.
And the other great thing I think about this, now that I've figured out how to use it really well, if you go under assignments, I have all of the homework and exams on this assignments tab. Now, when this says due on the exams, that's the end of the exam. It's just warning you the exam is coming and you must be done by that time. Or actually, this is the start time. These are all start times for the exam. For the homework, all the homeworks are due on that day at midnight, and they have their points value associated with them. So if you're in doubt of what's due when, go to the assignments tab in Canvas, and it should only give you the 1 or 2 weeks out, depending on how you have it set up. So everything is here, and then eventually everything will fall into the gradebook thing. So you will be able to see that. Your own grades, of course. All right, questions about the Canvas site? Okay, great. If you do, go ahead and email me. So this course, because it's condensed into a whole semester, we're going to hit a lot of topics, but we're not going to go very deep into them. So the idea here is to keep on, keep up with the homework, keep up with the reading. One way that some students find good is to go ahead and kind of read the book or skim the book ahead of time. So you're getting, you kind of don't understand everything, but you're familiarizing yourself with it, and then come to the lecture, and then you can ask questions if you have questions, and then look at the videos. Sometimes people look at the full videos and come for the lecture. It's however you best learn. If you're an audio visual learner, obviously the videos are better. If you're a book learner, obviously that's better. If you're kind of figure it out person, then that's where the homework comes in, and that's going to help you as well. So try whatever it takes to get you to have a, to kind of get this into your memory and get this into kind of a working order in which you can identify things. Oh, look, that looks very similar to this other reaction. Will that work? And so you should be able to see that. Hey, we're up to 60 participants. That's amazing. We're only missing one person. That's okay. All right, so that is our Canvas website. And that's a little bit about me. All of our exams will be on Top Hat. So you'll go to the Top Hat and you can hit the homework tab and go to those. Those will all be done in Proctorio. I know some people have had a really hard time with Examity, and so I've only had 3 minor problems with Proctorio over the last several semesters. So hopefully they've fixed all of those. Every once in a while, it'll lose a picture. Every once in a while, you'll have difficulty logging in. And every once in a while, it'll kick you out if you lean a little too far off screen. But I monitor them live, and I can get you back in and get you assigned an exam which you can take on that time. So all exams are done during class or during our regularly scheduled class time, and will be on Proctorio. All right, any questions about that? All right, so I'm going to go ahead and switch gears, and I'm going to head over to Top Hat, and I'm going to go ahead and start lecturing on the book. Okay. So from this point on, I'm going to start exactly at 11 o'clock. I'm going to hit that record button, and then I'm going to pick up where I left off on our lecture. Okay. So as we get through that, what will happen is I will also try to stop very close to exactly on time at 12:20. Your time is valuable, and I know you have other things to do. So I'm going to try to stop. If I'm not stopping, somebody kind of, by the way, it's almost time. So it's, so I do not run over my time. Okay. So I'm going to go ahead and take this one right here. I'm going to unassign it right now, and then I'm going to present the slides. Unassign and present. All right.
Dr. Irvin?
Yes.
On my screen for your computer, it's still on the Canvas page.
It's still on the Canvas page. Okay.
I don't know if anybody else is having that issue, but okay, yeah.
All right. What does it look like now?
It looks like Top Hat now.
Okay. Yes, Proctorio is in Top Hat. Well, you'll go, I'm sorry, I have a question about the thing. When you go to Top Hat for your exam, you will be assigned an exam, you know, exam 1A, 1B, 1C, whatever it is. And you just click on that and it'll ask for an image of your driver's license. It'll ask you to scan the room. And this is all recorded. It's not live monitored. And then it'll just monitor you over time. And if you don't pet the cat too much and, you know, you just look at the screen, you don't really get flagged. Every once in a while, somebody will walk across the back and it'll try to kick you out, and then I'll take you back in. Does that answer your question about Proctorio? From my understanding, it's much easier to use than some of the other sites, and there's very few problems. Okay, so what I can do here is I can also take attendance, and to take attendance, all it does is pops up this little code. So you can either hit the join code if you're on the computer, or you can text it by that number at the bottom. And so only 38 of you, it looks like, have signed up for Top Hat right now. So I'm not going to take, you know, I'm not going to take this as attendance, but it is an option I have that we have. So I'm going to just minimize and keep open just so you have it. Okay, so tried to register, asked me to pay. For the Top Hat, you should only be paying for access, which is, if for a single class, I think is like $24 a year, a semester. Or if you have the unlimited $100 package, then you should have access to it there, plus Proctorio, which should be approximately $10. There should be no book. All these materials are my materials, and so it should just be access and Proctorio. Okay. All right, so I'm going to go ahead and start presentation here. So all right, there it's starting. There we go. All right, I'm going to go back one slide. All right. So what we have here is organic chemistry. And the first chapter we're going to talk about is covalent bonding and shaping. Okay. So when we talk about organic chemistry, we're talking about compounds that contain carbon, and they have a specific way in which they bond, and understanding how they bond, why they bond, how many electrons are in each bond will tell us a lot about how reactive the compound is, which part of the molecule is going to react, and what those shapes of those molecules are. So we're going to go down this path and try to figure out, you know, can I just look at the periodic table and figure out how many bonds something has? The answer should be yes by the end of this chapter. Okay. So let's go ahead and just basically talk about, technically organic chemistry is a carbon with a hydrogen on it somewhere in the molecule. Okay. However, it can be broadly defined as anything with carbon in it. So there's millions and millions of compounds that have done this. Thousands of new ones are being made each day, some intentionally, some not intentionally. But the idea is that this is a very broad spectrum. But by using some certain procedures like nomenclature procedure and looking at where the different atoms show up on the periodic table, you can predict how these things are going to bond. You can predict which part's going to react, and you can predict what the shape of the molecule might be. For Top Hat, you shouldn't need an attendance code if you're already enrolled. If you haven't enrolled, you'll have to enroll before you can do that. So you should have received an email, an invite email from Top Hat saying, please join our course. If you did not receive an email of it for an invite, go ahead and email me and I'll resend one. Okay. So, sorry, just answering some questions in the chat. Okay, so that brings us down to carbon. Carbon is actually kind of a small atom. It's on the top row of the periodic table. It doesn't really have all that many electrons to it, but it is unique in the fact that it can form single, double, triple bonds. It's right in the middle of electronegativity, and I'll tell you why that's important. but it forms strong covalent bonds with hydrogen, oxygen, nitrogen, and sulfur, the halogens, and some metals. This leads to the wide variety of compounds we have, and it also can lead us to knowing the shape and what things will react in our system. Okay, let's see, there we go. Okay, so just to review regular chemistry, if you haven't been there in a while. Okay, so in the center of the atom, which is really, really small, that's where your protons and neutrons are. Your protons are positively charged, your neutrons are neutrally charged. So that's where all the positive charge of the atom exists, and it takes up very little amount of the actual space. In fact, if you put a golf ball in the middle of Bobcat Stadium, that's about the approximate size of where the nucleus would be and its approximate size. And the electrons would start around the outside of the stadium part. Okay, so that means there's this huge amount of empty space in the middle. Okay, so that's what gives us the volume of matter. The nucleus gives us the mass of matter. The electrons being flung around at near the speed of light, taking up this massive amount of space, is what causes it to have volume. Okay, so electrons are around the outside and they're going very fast and trying to fling themselves away from that positive charge. If they were to be attracted to that positive proton, they would combine to form a neutron and they would annihilate each other and we wouldn't have atoms. So you have to keep the electrons away from the proton enough so they don't collide, but close enough so they're attracted to each other. So this is the great dynamic. This is this sweet little, what we call a Goldilocks kind of planet where the electrons are just far enough away, they don't get sucked in, but just close enough that they balance the charge of all those protons. Okay. So that leads us to the idea that electrons have what we call shells. Okay, so don't think of it as an eggshell where it's hard and it stops exactly there. Think of it as a probability, or it's the electron is going to be in this kind of location 95% of the time. Okay, it's not hard that it's not a hard shell because the electron can be on this part of the shell at one moment, and then a couple seconds later it's over here. But when you average out all the places it has this electric field repelling other electrons. So don't think of it as a hard shell. Think of it as if I average over time, there's going to be enough electron density to take up that amount of space. Okay, so we have different energy levels associated with these different shells. Okay, so if we look at shells, they have energy levels. So we start with 1 being the closest into the nucleus, and we go out to the second shell, the third shell, and the fourth shell. So this is defined as our electronic energy level, okay, or principal energy level, okay? And we will be denoting that principal energy level with that large number at the beginning of these notations we have. The number here is going to be the energy level. The letter is going to be the shape we have. And then the number here is going to be the number of electrons we have. And we're going to look at that. So this first energy shell, because it's so close to the center atom and it's its lowest energy, it can only hold 2 electrons. The second energy cell holds 8 electrons. The third energy cell holds 18 and then 32. Now, for organic chemistry, most of the time, we only have to deal with those second shell electrons. That's why we're going to start to count to 8 for most of the times we build molecules. All right, so once we have our energy level or our shell level, now we have to think about the shape of the orbitals that are inside there, okay? So you have your energy level, that's the first number, and then we have the shape of the shell on there. So in there, we have the first orbital level. It's called an s orbital. It's a spherical orbital, okay? Shaped like a sphere. It can only hold 2 electrons, okay? Once we go up to the next energy level, we have another s orbital, but it can only hold 2 electrons. But we want to hold 8 electrons in that energy level. So how do we do this? What we do is we end up with 3 more orbitals, each of which has 2 electrons in it. And they're all about the same energy and they're pointing in different directions. When we go to the next level, we have to add a new shape of orbital, a d orbital, and those look more like clovers. And then we actually can go into the f orbitals if we have very big molecules. We're not going to do that, but they do exist. Okay. Let's see. Oops, not that. There we go. So if we start talking about energy levels, the lowest energy level is the one that's closest in, and then we start moving out. Okay. So if I said before, you can only put 2 electrons in this lowest energy level right here. Let me change to color. There we go. This lowest energy level here, we can only put 2 electrons in it. And so we only have 1 orbital where we can put those 2 electrons. But I said the second energy level has 8 electrons, okay? So we can put 2 in that s orbital, but now we have to have a place to put 6 more electrons. And that's where the 3 p's come out. We have the second energy level is 2, the shape of the orbital is p, but we have 3 equal in energy orbitals possible, okay? So that means that that s orbital is slightly lower in energy than those p orbitals. And we're going to use that to our advantage, okay? When we go up to that third level, the s orbital is again the less energy than the p orbital, and the p orbital is less energy than the d orbital. And so we can see that they start breaking out. The other thing this visualization does is it tells us how we're going to fill these orbitals. You always fill the orbitals at the lowest energy level first. So when we look at this diagram here, we know that our first electrons, 2 electrons are going to go here. Our next electron has to go in that s orbital. And then we put the next one in there. And then the next electron goes here. We have to completely fill these orbitals before we put any electrons here. So you always fill from the bottom up. Okay. All right. So now I said you can put 2 electrons in an orbital, okay? However, an electron has negative charge and an electron has a negative charge. And what happens when you put 2 of the like charges together like that? They repel each other, okay? We have that negative repellent or electron repulsion, okay? How can we get these 2 electrons to not repulse each other enough to occupy the same orbital? Not the same space, just the same part of space they can rotate around in. And the way we do that is what we call spin, okay? So every electron has either a +1/2 spin or a -1/2 spin. And if you've taken any physics, you might know that as you have an electric field moving in a direction, there creates a magnetic field around it, okay? So it has an electronic direction and a magnetic field, okay? So what we have is when you create that magnetic field of electron moving around, you now get a pole. You get a north pole and a south pole on that electron. Okay. So if you had 2 electrons and one was in the north pole and one was in the north pole, these would still repulse each other. First by the electronics, but now by the magnetics. So the magnetics are pushing against each other too. But what if you put a north pole and a south pole together? They are attracted to each other. Okay. So the magnetic attraction is overcoming some of that electron-electron repulsion, allowing us to do this spin pairing of electrons. Now, what this allows us to do is make sure that we have those 2 electrons in that orbital. So they're always going to be 1 up and 1 down. Okay. All right. So if we want to get crazy and think about where we're going to put all these electrons, we can actually do this setup here where, let's see, let's blow this up. That's not zooming in at all, is it? All right, let me just annotate here then. And, okay, so in this first energy level, we only have the possibility of putting 2 electrons in. So we have the 1 for the energy level, the s, because we only have spherical orbitals there, And then we have a 1 or a 2, depending on how many electrons are in there. And then that energy level is now full. Okay. Now, it's interesting because this is helium. Helium's a noble gas. And so it has a full outer shell. Okay. So that means we can cheat and say, oh, helium plus new electrons to describe all the next elements, right? So once we get to lithium and beryllium, we actually now have our our 2s orbital energy level is available to us. And we can put 2 electrons in there. So we go 1, 2. But now once we get to boron, we have to start putting electrons in that p orbital. So we put the first, second, third, fourth, fifth, and sixth electrons in that p orbital to go to the next filled shell, which is neon. And then we can do that again on the third period and go all the way down to argon. And see what we're doing here is we're adding electrons to the lowest energy shells first, and then the next lowest energy until the orbital is full, okay? Now notice in all of these right here, this full orbital is 8 electrons. This full orbital is 8 electrons. That number is going to become important, so write that number down. Okay, so let's try to find the electronic state for magnesium and argon, okay? So if we have magnesium, it's telling us it's atomic number 12, which means we have 12 electrons to assign. So we have to start filling our 1s. First thing we do is put 2 electrons in that. That's 2. Now we have 10 electrons left. Then let's fill our 2s, and that's 2 electrons. So now we have 4 electrons. So we have 8 electrons left. So then we have our 2p, and we can put 6 electrons in that p orbital. So that's 8, 9, 10. So that's 10 electrons. So now we have to go up to our 3. Ooh, 3. And that starts with our s orbital, and we're going to put 2 electrons in there. Okay. So now, just by putting all the electrons from the lowest energy to the highest energy, we can fill any of these orbitals. Okay. Now to complete the argon, we can just keep adding to this with our 3p orbital. And since our p orbital can take 6 electrons, we can add 6 electrons to 12 electrons. So we have now a total of 18 electrons for argon. Okay, do we see how this works? We just fill from the bottom up and we go in order. Okay, all right, so when we do this correctly, we're going to end up with 2 kinds of electrons. Okay, we're going to wind up with electrons. Oops, wrong button. We're going to wind up with electrons that are what we call core electrons. That means they have a filled shell. So like this helium, this neon, and this argon, those have full orbitals. And so if you add any more electrons onto that, all the other electrons are what we call core electrons, and they don't bond. So we don't care about them. So we need to identify the valence electrons, okay? So by definition, the valence electrons are the electrons on the outermost electron shell of the atom, okay? These are the ones that do the bonding. These are the ones we have to pay attention to. And so because of that, there's a great little visualization called the Lewis structure of an atom, or the Lewis dot structure, that lets us see only the valence atoms. And when we only see the valence atoms, that means we can start to add bonds around them and be able to get to a very defined, even if you've never made the molecule before, by doing your Lewis dot structure and showing where all the atoms are, you should be able to see where the bonds are. Okay, so let's go, there's some rules associated with it. So let's figure out how to do that. The first thing is you need to figure out how many valence electrons are on the atom. So instead of memorizing that, let's look at the periodic table instead. So on most periodic tables, there's what we call the A groups and the A group. And the A group is the one that tells us how many valence electrons are on the system. Let me see, I think I have a, nope, I don't, okay. So if you look at a periodic table, there's this 2 columns right here at the beginning, and then there's 10 columns of these transition metals, and then there's 6 more columns on this side, giving us a total of 8 columns here. Those are the A columns. These right here are the A columns. Okay. So if we look at A1, that's where hydrogen is. And then A2 is actually where helium is because it has 2 electrons in its outer shell. A4, meaning it has 4 valence electrons in its outer shell. So that's carbon and silicon. 5 is going to have 5 electrons, nitrogen, phosphorus. 6 is going to have 6 electrons, oxygen, sulfur. 7 is going to have 7 electrons, giving us the halogens here. And then, of course, the 8s all have 8, and those are our noble gases. Those aren't the ones that react. So just looking at the table of contents, periodic table of elements, you should be able to identify the number of valence electrons you have. Okay. So now that we've identified those number of electrons we have to decide whether or not the molecule has, how that molecule will bond. Okay. So does it bond by losing an electron or gaining an electron and forming an ion, or does it share those electrons? Okay. So in organic chemistry, there's actually a continuum of bonding. There are some things that are purely ionic, some things that are purely covalent, and some things are in the middle, and that's all based on their electronegativity. So if an atom gains electrons to fill a shell, it has more electrons than protons, and it becomes an anion. It's negatively charged. If an atom loses electrons to make the next shell down filled, it becomes a positively charged atom. Okay. Now, if we have a bond between an anion and a cation, or a plus and a minus ion, that's what we call ionic bonding, because the electrons are not shared. The electrons have been given away or taken to form those charges. In contrast, covalent bonds are when you share the electrons. It doesn't have to be equally shared, but if you're sharing electrons so that neither one has a full charge on it, that is a covalent bond. Excuse me. All right, so that means we can classify all of the chemical bonds in organic chemistry as ionic, polar covalent, and I'll talk about how you can identify the difference, non-polar covalent based on the difference in the electronegativity of the atom. Okay, so anything that says covalent means you're sharing electrons. Anything that says ionic means you have a positive or negative charge. Okay, so let's talk about those covalent bonds now. Okay, so electronegativity is a controlling factor. And again, you don't have to memorize numbers. You have to look at trends on the periodic table. Okay, so it's basically the measure of force of an atom's attraction for electrons. Okay, so what do we mean by that? Well, let's look at this row right here. Okay, these are the halogens. These halogens have 7 electrons of the 8 electrons to fill their shell. Okay, all of these, all they need is 1 electron to fill that shell. Okay, which means that they have the highest electronegativity, because if they fill that shell, they'll have a negative charge, but they'll be completely happy and full. Okay, so these numbers range from fluorine being around 4 to rubidium, which is down here, which is like 0.75. Okay, so the numbers go from 4, there's a decimal point there, to there. And they follow the trend. Electronegativity increases as you go up the column and as you go across the row, making fluorine always the most electronegative. Okay, and then it drops off as you go from there. Okay, so what does that mean? What that means is that fluorine is the most electronegative, and then oxygen's a little less electronegative. Nitrogen's less electronegative still. And then carbon, which is the one we're going to deal with, is less electronegative than fluorine, but more electronegative than some of these other things, including hydrogen. Okay. So that's going to tell us whether or not we're going to share electrons or give electrons away. Okay, so let's look at the full periodic table and look at those group numbers again. We have group A1 and group 2, 1A and 2A. That means that these have 1 electron in their valence shell. These have 2 electrons in their valence shell. 3, 4, 5, 6, and 7 electrons in your valence shell, okay? And we can use that same trending for our electronegativity. This group over here has the highest electronegativity, and these are about the same. These are the next row down, and then we start to see them drop off a little bit here. Hydrogen's a little bit of an outlier. It's about just a little bit lower than carbon. And then as we go to here, everything over here, we're probably going to start forming ions because the numbers are much, much lower than that of fluorine. Okay. So what would the definition be of a nonpolar covalent bond and a covalent polar bond? Well, if the electronegativity difference between the two atoms is very small, then neither one is trying to pull electrons away from the other one. So for example, hydrogen has an electronegativity of 2.1. Carbon has an electronegativity of 2.5. The difference between them is 0.4, okay? Which means that the hydrogen doesn't really pull electrons away from carbon, and the carbon doesn't pull electrons away from the hydrogen. So we have a nonpolar bond. They're equally sharing those electrons between those two atoms, okay? Now, the next thing up is something, let's do, let's see. We have oxygen here and we have carbon here. Oxygen is 3.5 and carbon's 2.5. So that puts us into what we call the polar covalent. It's between 0.5 and 1.9, okay? So they means that the oxygen is more electronegative than carbon, which means it's pulling some of the electrodensity away from the carbon, giving us a polar bond. Polar bonds are more reactive than non-polar bonds. So we can use that to our advantage when we're looking at reaction schemes. Now, if the difference in electronegativity is 2 or greater, they typically form ionic materials. And you think metals and nonmetals, and that's what we'd see, or salts that you would find, okay? So what we'll be dealing with in this course is mostly the nonpolar covalent and the polar covalent, because we're going to deal with stuff in that upper corner of the periodic table. Notice these are all pretty close together. This is where we're going to deal with our particular materials. Okay, so if you have a electron negativity difference, how does that affect where the orbitals are? Well, if we looked at sodium, we filled up our 1s, we filled up our 2s, we filled up our 2p, and we have 1 electron in that 3s orbital because it's in a 1a column, okay? So it has a half-filled orbital, okay? And this half-filled orbital is slightly higher energy than this 2p orbital down here, okay? Now let's look at fluorine. We filled the 1s, we filled the 2s, and we have 5 electrons in that 2p. It's 1 electron away from filling that orbital, okay? And it's very electronegative, so it can handle having that negative charge. So what it's going to do is it's going to pull away that higher energy electron from this outer orbital of sodium, and transfer it to its almost filled orbital in fluorine, okay? So what that means for us is that it will give us a full electron shell and a positive charge. And then this fluorine, come on, there we go, is also giving us a full electron shell and a negative charge. So now we have 2 driving forces here. 1, electronegativity. 2, you have complete filled shells, okay? And that's why certain atoms will have certain charges. You're trying to get the charge that gives you that full shell, okay? So when we transfer that electron from one to the other, we have now ionized a material. We have a positive atom and a negative atom. So that's a full ionic bond. In covalent bonds, we're actually sharing those 2 electrons in between the 2 different atoms. Okay. So let's look at a simple one first. Let's look at a hydrogen molecule, okay, the diatomic hydrogen molecule. So each hydrogen has 1 electron and it's 1 s. It wants 2 to fill that shell. So what it's going to do is it's going to equally share this electron from this hydrogen with this electron with this hydrogen. And when they share them, they're now both, because they're sharing electrons, have 2 electrons. They have full shell when they work together. Okay. Now, what this means is because we filled the shell on each, it actually saves energy to have that bond form. Instead of having the 1 electron by itself and the 1 electron by itself, by sharing and making this bond, we actually save energy. And that's the driving force for all bond formation, is we're trying to save energy. Okay, so that's if they're the same. So in this case, because they both have the same electronegativity, this is a non-polar covalent bond where the electrons are evenly shared between both atoms. Okay, what if you have 2 things, like in this case, HCl? HCl, hydrogen is less electronegative than chlorine. Chlorine's about 3.5. Hydrogen's about 2.1. So it's still not ionic, but it's still making a bond, but it's polar. Excuse me. So the one that's more electronegative is going to be pulling some of the electron density from that bond toward the more electronegative atom. In this case, we have the chlorine side of it pulling electron density, giving it a partially negative charge. That's what this delta minus means. It's not a full charge. It's not an ion. It's just partially negative. And then on the hydrogen, because it's the less electronegative, its electron density is being pulled in that direction. So that makes this partially positive. Okay. It's still a covalent bond. The difference in electronegativity isn't high enough to ionize, but it's not equally shared between those 2 atoms. Okay. Now, this polar bond gives us reactivity, and so we need to pay attention to that. The other thing it gives us is, if part of this is partially positive and part of this is partially negative, and we have something coming in to react with it, and that something coming in is positively charged, we know which side of the molecule it's going to interact with first. This already has a positive charge, so it's not going to attack this side of the molecule. It's going to attack the partially negative side of the molecule. Okay, so knowing the polarity of a bond tells us which side something coming in is going to attack on that bond. So it's very important to pay attention to that. Okay, let's see what time. All right, plenty of time. All right, so now let's figure out how to make any structure possible just by throwing a bunch of atoms at you. Okay, so we have to just follow a nice little process for this. And if we follow the process, we get to the correct answer 99% of the time. Okay. So the first thing we need to do this Lewis dot structure is to determine the number of valence electrons in the molecule or ion. Okay, so what that means is that if you have 2 carbons and 2 oxygens in your molecule, you have to add up all the valence electrons for each of the atoms. Okay, so remember, it's that A number, A column number tells you that. All right, the next thing you do is determine the connectivity or the arrangement of those atoms. And generally we do a certain thing where we put the least electronegative atom in the middle and build out from there. And I'll show you how to do that. The next thing we do is we connect the atoms with a line. Okay, that atom with a line means we have a bond there. A single line is 2 electrons, and it's a bond between those 2 atoms. Then we sprinkle in all the rest of the electrons that we can, and then we try to figure out if we have enough electrons around each and every atom individually. And if we don't, we either can have them show up as not bonding electrons or give us a second bond, a third bond that we'll see in our system. So let's do this step by step and do a few examples here. Okay, so the first example we want to do is something simple, water. Okay, So if we look at the electronegativity, oxygen is much further to this side of the periodic table and much higher than hydrogen. Hydrogen's way over here. So that means oxygen is going to be the middle of our thing. It's the least electronegative atom we're going to put in the middle. And we have H2O. And so we have one electron for hydrogen, one electron for the other hydrogen. So we have two. And oxygen is in group 6A, which means it has 6 electrons. So we have a total of 8 electrons to play with. So the first thing we do is we put our electronegative atom in the middle. We add our 2 atoms here. And we have now consumed 1, 2, 3, 4 electrons, which means we have 4 more electrons to put somewhere. So we're going to put those 4 more electrons on the most electronegative atom, and that gives us our starting material. So these electrons we're just counting as the bonds. Okay, so now we need to see if our structure is done, and we do that by looking at how many electrons are around this. So if we look at, we have a total of 8 electrons around oxygen. So this oxygen has an octet. We have 2 electrons around hydrogen. That's what hydrogen wants. So hydrogen's happy, oxygen's happy. We have a nice Lewis dot structure. Okay. So let's do this carbon one again. Instead, let's do this one down here. So carbon is in 4, so it has 4 electrons on it. And then we have 4 hydrogens. Each of them has 1. So we have a total of 4 hydrogen electrons. So that gives us a total of 8 electrons. So we're going to put our carbon is the least electronegative. Well, hydrogen's never in the middle because you can only bond to it once. So we're going to put carbon there, and then we're going to put the 4 hydrogens out around here. Now we have to go back and make sure we have all of our electrons accounted for. Okay. So if each of these bonds is 2 electrons, that means we have 2, 4, 6, 8 electrons. We needed 8 electrons. That means we have a correct Lewis dot structure. Okay, let me do this last one of ammonia and then we'll move on. Okay, so nitrogen is in group 5A. If we look at the periodic table, that means nitrogen has 5 electrons. Okay, we have 1, 2, 3 hydrogens. So we have a total of 3 electrons with hydrogen. Okay, so that's 8 electrons again. So all of these have 8 electrons. So, but they all look different because they're all building different things. So let's put the nitrogen in the middle again, and then we'll start with our bonds. We have 2 electrons for this bond, 2 electrons for that bond, 2 electrons for that bond, for a total of 6 electrons. That means we have 2 electrons left over. Okay, we don't need to make another bond because we have all of our atoms bound together. So we put the remaining electrons on the most electronegative atom, which is nitrogen here. And so we can have that non-bonding pair of electrons. A lot of time I'll call it the lone pair or the non-bonding pair of electrons. That's telling us something about the shape of the molecule. Okay, so that's why we always draw that non-bonding pair in our Lewis dot structure. All right, questions on Lewis dot structure. Count the number of electrons you bring to the party, get everything bound together by at least 1 bond, and then start counting, filling in the rest of your electrons. So that's the first steps of it. All right, so what if you end up with not enough? Okay, for example, let's do this one right here, ethylene. And we have 12 electrons, and those 12 electrons come from 1, 2, 3, 4 hydrogens. That's 4 electrons. This carbon brought 4 electrons, and that carbon brought 4 electrons. So that's a total of 12 electrons. So if we use our rules and draw out our carbon here, and our carbon here, and our hydrogen here, and our hydrogen here, and our hydrogen here. So we've just put our least electronegative atoms in the middle. We've added all the hydrogens to the outside. Now let's count how many electrons we have. We have 1, we have 2, 4, 6, and 8, and 10. So we've accounted for 10 of our electrons. Okay, we have 2 electrons left. So what are we going to do? We're going to put 1 of these last electrons here and 1 of these last electrons here. Okay, so we're done, right? No. Let's count how many electrons are around each of those carbons and see if they're happy. Okay. So if we're looking at just the electrons around the carbons here, we have 2 electrons for that bond, 2 electrons for that bond, 2 electrons for that bond, and 1 electron for this right here. It only has 7 electrons around it. It wants 8. So we're not done yet. Okay. But how can we do this? Well, if we move this electron in here and this electron in here to get that double bond, then we'll end up with both of those electrons contributing to giving us our second bond. Now let's count electrons again. 2 electrons for this bond, 2 electrons for that bond, 2 electrons for that bond, 2 electrons for that bond. We have 8 electrons around carbon. It's happy. And we do the same one for the other carbon. We have 8 electrons around that carbon. It's also happy. So just by taking those electrons that we put in there and using them to make our octet around our atoms, we knew that we had to draw a second bond or a double bond. The same thing works for acetylene. If we count the number of electrons around here now, if we count the number of electrons around this carbon on this side, we have 1, 2, 3, 4, 5, 6 for that triple bond, plus 2 more is 8. And the other side is the same way because we're going to share these. Okay. Does everybody see how we do the process? Number of electrons, try to get bonds to everything, sprinkle the last electrons in, and then try to get 8 electrons around each of the atoms that aren't hydrogen. And then that gives us our Lewis dot structure. Okay. All right. No typing in the chat. All right. So here's some rules that'll help you along. Number 1, hydrogen only ever has 1 bond, and it's rarely the center of the molecule because it only has 1 bond. Number 2, carbon always has 4 bonds. They can be double bonds, triple bonds, but they all always have 4 bonds and no unshared electrons. Nitrogen will typically have 3 bonds and 1 unshared pair of electrons if it's a neutral molecule. If it's a charged molecule, it might use those electrons to bond to something else. Okay, so this only counts for neutral molecules. Oxygen, because it had 6 electrons already, it only needs to share 2 of those, so it makes 2 bonds. And then it has 2 unshared pairs. Halogens, because it has 7 electrons, only needs to share 1 of its electrons to make its octet. So it'll have 1 bond and 3 lone pairs. Okay. Now, if you add charge to it, you gotta pay attention to that. Okay. So once we have our Lewis dot structure done, and we think it's a molecule or an ion, we need to identify what is the actual charge on each and every atom. And that's called the formal charge. So what this does is tells us if there's a positive charge residing on an atom within an entire molecule. Okay. And we have a simple formula for that. We have this formula here at the bottom. We're going to do formal charge of the atom is equal to the number of valence electrons right here. So the number of valence electrons are those electrons you brought to the party for the Lewis dot structure. Then you have to subtract after doing this math function first. You want to take all unshared electrons and add them to 1/2 of the shared electrons. Why 1/2 of the shared electrons? Oh, wait, that's a covalent bond. So that means one of those electrons belongs to one of the atoms and one of the electrons belongs to the other atom, but we're sharing them. So we only can use 1/2 of that to counterbalance the charge of the nucleus. So we can only use 1/2 of the bonded electrons or shared electrons. Now, once we do this math procedure first, then we subtract that from the total number of valence electrons, and that's going to equal our total formal charge. I mean, our each atom's formal charge. Okay. So let's do a couple calculations for this to make sure we understand. Now, in this case here, we have this nitrogen with 4 hydrogens on it and a positive charge. Okay. So let's figure out how many electrons, what the formal charge around nitrogen is. Maybe hydrogen's carrying that positive charge. So formal charge is equal to the number of electrons it brings to the system. And so it brought 5 electrons because it's in group 5A. And then we have to subtract from that non-bonded electrons. In this case, we don't have any lone pairs, because if we drew the Lewis dot structure for this, we would have nitrogen with 4 hydrogens bonded around it. And the net molecule has a positive charge, but we're trying to identify where that positive charge is. Okay. So we have 0 lone pairs plus 1/2 of the bonding electrons. So we have 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here, which is a total of 8. Okay, so that means we have 5 minus, after we do the math inside the box first, we have 4, means our formal charge is plus 1. So that means the nitrogen is where that positive charge is. Okay, so it's not on a hydrogen, it's actually on the nitrogen because the way we've done it. Okay, so let's do this neutral molecule here and see what it does. Okay, so the first thing we do when we do that is we draw the Lewis dot structure for this. Okay, so if we're going to draw the Lewis dot structure, we have carbon right here, we have oxygen right here, we have 4 electrons right here on the carbon, we have 6 electrons on this oxygen. Okay, so we need to make another thing. So maybe we need to make a triple bond here somewhere. So we have carbon with 3 bonds to oxygen. And that gives us 1, 2, and a lone pair here, and 1 electron over here. Does that look like a good Lewis dot structure? Or 2, yeah, let's see, yeah. No, because 1 bond here, 1 bond for this electron, 1 bond for that electron. So yeah, that gives us our thing. So now we can calculate formal charge for oxygen right here. And we know that formal charge is equal to the number of electrons oxygen brought to the party minus its lone pairs. So there's 2 electrons in a lone pair. And then 1/2 of the regular electrons. So we have 1, 2, 3, 4, 5, 6 bonds. So that's 6 electrons right there. That means we have 6 minus 2, it should be a plus, sorry, plus 3. So that means we have a formal charge of plus 1 on oxygen. And if we do it for carbon here, we're going to have 4 minus bracket 1 plus 1/2 of 6, because there's 6 bonds there, is equal to 4 minus 4, which is equal to 0. So it should have a formal charge of 0. Okay, do we get where that's coming from, right? So you calculate formal charge on each atom. And the reason we do this is it tells us exactly where the charge resides. It doesn't reside on a hydrogen here. This negative charge is actually on 1 of the nitrogens, not all 3. This positive charge, turns out it's going to be on the nitrogen if we do that calculation. So go ahead and do the Lewis dot structure for a couple of those and show yourself where that positive charge is. Okay.
Would it be possible to see the equation from the previous slide one more time?
Yes. Okay. So the equation is formal charge is equal to the number of valence electrons minus, and this is in brackets, you have to do all this math first, and then the unshared electrons, which can be single electrons or lone pairs, and 1/2 of those that are bonded. Okay. And there's a couple examples of this in the homework, so you can get some practice on that as well. Okay. All right. So once we have our, I'll let you. Okay, actually, yeah. So this is a bunch of different ways that we can actually draw the different Lewis acceptable dot structures. Notice in the one we did here, it actually had an electron that wasn't paired. Probably is not going to do that. I think I left out an electron somewhere. So, but in this case here, these are possible Lewis dot structures. And if you drew, and if you go and calculate the formal charge for each of these, it'll actually tell you what is most likely to be the system. Okay. So for example, if we were to do the Lewis dot structure for this, this would be, I'm sorry, the formal charge for this carbon is going to be +1, and this one is going to be -1. 1, 2, 3, 4, 5. Yes. And then if you go back and do the calculations for each of these, you'll see which one's going to give us the most like a neutral species, or where the different charges might move back and forth. So go ahead and do that. Calculate the formal charge for each of these species, and that will give you a great practice in calculating that. Okay, so that being said, we've now figured out how to draw our Lewis dot structures. Okay, we take the number of electrons we have, make sure they're equally spread out, and try to have them, in a nice logical fashion, and if at all possible, have zero charge on as many atoms as possible. Okay, once we have our Lewis dot structure, now we have what's probably its most stable form. It's going to be the one without charges and the one where we have paired electrons. Now we get to talk about what that effect has on the shape of molecules. Okay, and when we talk about the shape of the molecules, it's called the valence shell electron pair repulsion concept. Okay, so we're only looking at the electrons in the valence shell. That's the first part. We're looking at them as pairs, meaning bonds or lone pairs, and that they have repulsion. Electrons are negatively charged and they repulse each other. What that means is if you have something with electron density in it, and it's fixed in space, it's going to try to get as far away from the other electrons as possible. So think of it as you grab 4 balloons and squeeze them together. They're going to form a tetrahedron because they're going to try to spread about as far as possible. Because remember, those shells are not hard. They are a place in which electron density might be. They are a place that's negative. And so they're going to spread out as much as they can. So let's kind of, I don't want to zoom out. All right. I need to be able to do this. So if we have 4 regions of electron density, okay, that means that we have 4 places that have a total of 2 electrons each. We're going to end up with what we call a tetrahedral electronic structure. Okay, now I said electronic structure. Okay, that's very important because if you have a bond, that's going to give you a different molecular structure than if you have a lone pair. So if you have 4 places of electron density, they're going to try to spread out as far as possible apart, and that's a tetrahedron. That's with 3 on there and 1 sticking up, kind of like some jacks. And they're going to be spread about as far apart as they can is 109.5 degrees. So in 3-dimensional space, if you're trying to spread these things out, that's as far as they're going to spread out. And we see that in something like methane right here. So we have 4 hydrogens, we have 4 bonds on that carbon. They're all the same. It's a nonpolar bond, and so they're all equal, which means the angle between any 2 hydrogens on this methane is 109.5 degrees. Okay, what if they're not equal? If they're not equal, then that changes the shape of the molecule. For example, if we look at this nitrogen molecule here, It has a total of 4 electronic places because this lone pair takes up space just like a bond takes up space. So now we have a 1, 2, 3, 4 electronic system. So they're trying to be 109 degrees apart, but they're not exactly equal. And if we look at the molecule shape, we only have a nitrogen with 3 hydrogens off it. And that gives us what we call a pyramidal shape, okay? Because this is an electron, but there's nothing bonded to it. So the molecule itself is a pyramid, okay? If we extend that one thing further in oxygen, now we have 2 lone pairs that are out here. So electronically, we have a total of 4, okay? But the shape of the molecule is actually bent because those electrons are taking up space above, but it still has those 4 electronic zones, making it try to be at that 109.5 degrees. Now this angle varies as we move, and I'll get to that in a minute, but they are going to try to achieve that 109 degrees. What if you only have 3 regions of electron density? If we have 3 regions of electron density, right here, we have what we call trigonal planar. So it's 3 things sticking out, and that's actually 120 degrees. Even in 3-dimensional space, them all in a flat plane at 120 degrees apart is as far as you can get them apart. So that leads us to the shape of new molecules. Excuse me. So in this case here, we have one, there we go. We have 1 electronic zone, 2nd electronic zone, and because the electrons are shared with this carbon in a double bond, that's our 3rd electronic zone, meaning that the angle between these 2 hydrogens is 120 degrees. The hydrogen and the carbon is 120 degrees, but it makes it what we call a planar molecule. It has to lay flat. It's spread out at 120 degrees from each other, and so it gets its shape completely from the fact that it has 3 electronic zones. And the same is true if we do something else like this. This is a flat planar molecule, and these are trying to be at 120 degrees apart. What if you only have 2? It turns out in 3-dimensional space, if you only have 2 things, you basically have a line. They're as far apart as they can be. Any other angle is less than the maximum that can be apart. And therefore we could have linear molecules like carbon dioxide and acetylene. Right here. So if we only have 2 regions, we have that linear space. Okay, so make sure you tell the difference between electronic density regions and molecular shape. Okay, so let's dig a little bit more into that, that 4 electronic zones. So our thing saying if we have 4 electronic zones, we're going to try to spread those electronic zones out as much as possible. So in the case of 4 equal bonds, in the case of methane here, oh, it kind of goes off screen there. Okay. These are all equal, and so they're going to be that 109 degrees apart. In the case of the nitrogen, we have this lone pair. This lone pair actually takes up more space than the bond to hydrogen. Therefore, it pushes those hydrogens closer together. It's taking up more space, and so our bond angle goes down. We actually go down to 107, okay? Because it's not shared between 2 atoms. It's not forced to be right in between those 2 nuclei. And so it spreads out a little bit. And then if we go to water, it does it again. We have these 2 electronic zones being slightly larger than the ones that are bonding, and we end up with a smaller angle of 104.5 degrees. Note that these are all tetrahedral electronic zones, but we have a tetrahedral molecular, a pyramidal molecular, and a bent molecular because of the lone pairs. Okay. It's a little bit easier in the trigonal planars because all you're really worrying about is kind of molecular size. So hydrogens are smaller than the oxygen. Therefore, this is going to take up a little more space, and therefore the angle between the hydrogens is going to decrease from the 120 degrees it wants to be, but the angle between the hydrogen and the larger oxygen increases. Okay, so it's all about the size of the atom that changes the angle from that ideal 120 degrees. Okay, we see that in ethylene too. Even though these carbons are the same size, the carbon is still bigger than the hydrogen, and therefore we have a slightly smaller angle between the two hydrogens and a slightly larger angle between the hydrogen and the carbon. However, look at the side view right here. Both molecules are perfectly flat and perfectly planar. And we can use that to our advantage in the future. Okay, which brings us to our last one right here. This is our linear. Okay, so we technically, you might think, well, look, there's a zone here and there's a zone here. But if we look at the zone around carbon, we only have the one on this side and the one on this side. That means we only have two electronic structures around carbon, making that a linear molecule. Okay. Now, if we look at the electronic zones around oxygen here, it's trigonal planar. But because we're talking about molecular shape, the electron density here, these aren't bonds. And so we only care about the bonds, the linear nature of the bonds, giving us that linear molecule. And then we can extend that out with acetylene having 3 bonds in the middle. That makes one electronic zone here, one electronic zone here, giving us our linear function over this section. And then if we go to the other side, we have one section here and one section here. So the other half is linear as well, making the entire molecule linear. Okay, so that takes us up to predicting the shape of these just based on their Lewis dot structures. So let's go ahead and do this one and this one before the end of the class today. So let's do the nitrogen one first. Okay, so because it's positive charge, we know that it's got 4 hydrogens around it. We calculated the formal charge already, showing that we had 4 equal bonds to hydrogen, and the positive charge is actually carried on the nitrogen. So if we have 4 equal bonds to hydrogen, that means we have 4 electronic zones that want to be in that tetrahedral pattern. But we also have 4 bonds to our system. So that means that because we have those 4 equal bonds and the positive charges on the nitrogen itself, we predict these angles to be tetrahedral, that's it, and at 109.5 degrees. Okay, so let's do our Lewis dot structure for this one over here now. Okay, so we have our carbon. Since we have 3 hydrogens drawn there, I'm going to say 3 hydrogens here. Okay, then we have oxygen, and then we have hydrogen here, right here. So we have a linear molecule, right? Wait. This isn't the right Lewis dot structure, is it? Right. We got to put our electrons, our lone pairs in here. Oh, that's going to change things. Okay. So let's look at the carbon first. We have carbon first. It's got 4 electronic zones and 4 bonds. So that means this carbon is going to be about 109 degrees right here. But it's actually, this is going to be a little bigger than 109 because the oxygen is bigger than the hydrogens. And this angle is going to be a little less than 109.5 because they're being forced out by this oxygen. So technically, this is still tetrahedral, but we know that the angles are going to be a little different than this, all of them being the same. Yeah. Now, let's look at the oxygen. Let's redraw the methane. Let's redraw the oxygen with lone pairs up here and the hydrogen down here and the CH3 over here. Now we have this lone pair taking up space, this lone pair taking up space. So electronically, we're still tetrahedral. However, Molecularly, we are now bent right here. And because these two are taking up bigger, more space, this is going to be less than 109 degrees. Okay, because these lone pairs are taking up more space than the one. So this bond angle between this is less than 109.5 degrees, and it gives us a bent molecule. You were saying that it's tetrahedral for carbon and oxygen molecules. Yes. When you have 4 electronic zones, you are tetrahedral electronically. Now, to be molecular, the shape of the molecule is how many bonds you have, how many atoms are on there. The lone pairs just tell you what it starts at, but by having those lone pairs not be bonding, the molecule is based on where the bonds are. So in this case, the carbon was tetrahedral still, but this oxygen is bent. And if we had 3 things to there, and it was still a tetrahedral electronic structure, we would have a pyramidal. We'd only have 3 bonds to it. Okay.
So the H3 carbon, tricarbon, trihydrogen carbon, that is its own zone.
Yeah. So if we look at that one real quickly here, because we're right on time here, we would have the nitrogen look like this and bonded to a carbon, but it would have a lone pair up here. Okay. So electronically, it has 4 zones, but it has a lone pair, making the molecular structure around nitrogen pyramidal. Okay. So that's why I say electronic structure is one thing. All of these have electronic structure tetrahedral, but molecular structure is over here bent, over here tetrahedral, and for this, I'm sorry, tetrahedral, this is pyramidal. And this was tetrahedral. Okay, so go ahead and review that, keeping in mind it's different between electronic and molecular structures. Okay, and I'm gonna stop here. I'm gonna go ahead and stop recording. And if you wanna hang back and ask a couple questions, that would be fine. It doesn't let me, okay, I'm gonna stop sharing and